OSI model because I think people sort of memorize it in a way that maybe interferes with understanding rather than helps it. Um, but I need to talk about it a little bit because the three protocols that I'm going to talk about are RSTP, which RSTP is used by layer 2 switches, but it's used with flooding to fulfill the same role as the other things that I'm talking about. So this is layer 2. Okay. Huh? So this is layer 2, and then OSPF and ISIS or ISIS. These are layer 3, and only these two are IP. I mean, this one isn't only IP, but a lot of people use it on IP networks. This one, when I talk about it, it doesn't route IP at all, not in the way I'm discussing it. So anyway, one of the problems that I have with the layers is I think all of the interesting stuff happens between the layers. So people will tell you that layer 3 is IP or CLNP for OSI, and layer 2 is Ethernet MAC, and layer 1 is like wires, which bit is transmitted first, what frequency is it transmitted at electrically, and stuff like that. But this isn't helpful because the interesting stuff is in here with wireless. You have all kinds of mess, like wireless stations register their MAC address on layer 1, and they do retransmission. So the 802.11, when you send an 802.11 frame, the access point will acknowledge the frame. If it doesn't receive the frame, your card will retransmit it inside the firmware in the card. So this is something that 802.11 does because it's layer 1, the radio, is so unreliable that it wouldn't work well without this, and the retransmission algorithm knows something about how long is it going to take the packet to get there. The timeouts are really short because it's the speed of light, and they're working around the limitations of the radio to make it usable. But they're using layer 2 stuff to do it, so they've modified their layer 2 to accommodate for this crappy layer 1. And they did it in a way, I don't know if you've ever tried to set up a wireless station card. It has to be like this. It's not possible to put more stuff behind here. Like, if you use Linux bridging or something on your wireless station card, and you try to bridge your station onto an Ethernet and then plug somebody else's computer into it, it won't work because a station gets one MAC, and then all of it's registered with the access point. Does this make sense? All right. Do you see the problem with the layer 1 and the layer 2? That because we have this unreliable layer 1, now we have problems bridging stations onto Ethernets. So this is confusing. It's a layer violation. The other thing that we have in between layer 1 and layer 2 is on half-duplex Ethernet. There's the we have 802.11, and there's a whole mess in there. Then we have CSMA-CD, which everyone's heard about, but which is not used on almost all modern networks because there's switches with full duplex. But if you have a half-duplex network, because of the way the wire works, you have this MAC layer procedure to retransmit frames if there's a collision. Um, and there's um, there's broadcast and NBMA. Um, your layer 1 and layer 2 combination has to accommodate sending a broadcast to all the stations. There's a lot of telco layer 1, layer 2 combinations that have multiple stations on layer 2 network, but they can't do broadcasts. So you have to send to each. And I think Token Ring is like that too, but I'm not sure. Um, anyway, this shows the confusion with the model, but I think maybe I talked about that too long because the interesting stuff is in here. Um, the model wants you to think of layer 2s as being underneath layer 3 and interchangeable. So I'm going to choose to use IP, and then I can pick whatever layer 2 I want. I can pick Ethernet, ATM, plain serial T1, token ring. Well, I guess token ring is sort of an Ethernet-ish MAC, but it's interchangeable, and it's not, because if you choose Ethernet or token ring, then in between here you use ARP. If you don't, then you have to use something else like ACLC or PPP. What do they call that? IP control protocol. So where does ARP go? Is ARP a layer 2 standard? Because if I'm using IPX over Ethernet, there's no ARP. Or is it a layer 3 standard? Because if I'm using IP over T1, there's no ARP. So anyway, the OSI model sucks. But back to this. Maybe you have some background now about why I'm grouping these things together. Because there's something else essential that all three of them do in the way that they're used in practice. So let's see. What shall I talk about first? So let's talk first about the flooding. Does that show through the back? So if you have a network of switches, and then you have some stations attached to them. Maybe I should give them numbers. The promise of an IGP is that if station 5 wants to send a packet to station 2, that these switch intermediate systems will know how to route this packet. And the way that switches operate is all routing is based on the destination address. What you're trying to reach is the destination. So we have a packet that's from 5 to 2. Routing looks at this, and learning looks at this. So this packet here, packet A, will go here. It goes everywhere. So there's no routing information for how to reach 2. But learning, as this packet is flowing through, is looking at this 5. So as this packet A passes through, this switch learns that 5 is in that direction. So if this switch needs to send something to 5, it won't bother sending it out here or here. And this switch here learns at 5 this way and this one. So now, if somebody sends packet B from station 4 to station 5, is this diagram getting too busy? It's bigger? It's going to be a little bit of a struggle. But, I don't know how long its memory is. It's configurable and it's not extremely important because there's, for the purpose of this discussion, there's other times when the memory is cleared. But there are some imaginable cases where, like if a station moves from here to here and the stuff that is remembered is wrong, then yeah, that's kind of a problem. But when you send out the new packet, it'll clear the other information out of the way. I don't have any diagrams or cases for that, but all right, so here we were with packet B. We've already learned from packet A. So packet B is trying to reach station 5. So it goes to this switch, and packet B goes only this way. It does not go here like packet A did. And then it reaches this switch, and it goes only here. It doesn't go this way. So now it's going straight through, whereas before it was flooded. So that's what I mean by flooding and learning. And this is not completely part of RSTP. If you just go by what the acronym stands for, it's the spanning tree protocol. There's no spanning tree here. This is just regular switches. But the spanning tree doesn't work without understanding this philosophy of routing. So let's see. Any questions about this, or can I move on to the spanning tree?
Now, are these is this information that's encoded in the actual data packets, or is this a separate packets that are just finding the routes for you?
All right, the question was, are packets A and B data packets, or are they routing packets? And the answer is, until you introduce RSTP, there are no special control plane switch packets. All of these packets are station-to-station data packets. So the idea is, if you don't have this learned information, then you can't route the packet and you just flood it everywhere. So if you have a huge mesh of switches and no stations plugged into them, before we've introduced RSTP still, if you ignore that, then there's no traffic at all, and the switches don't know how to reach anything. So they rely on that when you first plug in a station, usually it asks for a DHCP query or something, and then that gets flooded out. Well, I don't know. There's other cases because like this B packet, learning is operating on this. But only these two switches have learned about station 4. So if station 1 sent a packet to station 4, then it would be flooded to station 2. But if station 3 sent a packet to station 4, it would go straight to station 4. Does that make sense? So it's backwards because the learning looks, it's a little bit confusing because the learning looks at the source and the routing looks at the destination. So in the first case with packet A, everybody learned about station 5, learned routing information for that. But with packet B, not everybody learned about station 4. So it's kind of heuristic, like a memory cache or something. Anything else? No, maybe? Okay. All right, so the spanning tree is if you have um, this is a real problem for flooding because when you start with this first packet A and there's no information for station 2, then let's say station 2 is here and station whatever it was, 5 or something. Packet A goes here, and then it goes here, and then it goes here, and it just keeps going. And it causes a storm. So um, the there's no hop count or anything with these switches because hop counts are in layer 3. What can they do? Uh, so this is impossible for switches. This can't even happen even briefly. It'll shut down the whole network. And if you read the manuals for switches, this is the thing that I hate about them most, is they keep saying, if you make this configuration, it could cause a storm. And there's some bug and it caused a storm. And there's like a dozen things that you need to not do if you don't want to have a storm. And it's like maybe the storm isn't my fault anymore. Maybe this is not a good way to do things, but uh, people run switches without storms all the time. But the point of RSTP is to break one of these links. If you break this one, then A can be, then you have the same diagram that I had over here, where it's just one link, 2 links, and there's no more storm. There's no loops in the topology of switches, which is what you probably heard before. So I think I need to talk about the difference between a tree and a graph. Who needs me to talk about that? Some of you probably don't want to hear it again, but somebody? Yeah? Okay. So a tree is something that doesn't have any loops in it, but trees in computer science grow down instead of up like in the forest. So a tree can have, it has a notion of ancestry, like there's parents and children. It has a direction that it grows in, and that's enough to prevent it from having loops, and you can have as many children or as few children as you like. A graph can have anything connected to anything else. And there's directed graphs if there's an arrow here, and undirected graphs if it's just edges. So in general, the way this is going to pan out is switches need to have a tree, and the 2 layer 2 routing protocols can deal with graphs. So I think what I'll start with is what implications does that have for optimal routing or even just sane routing? Is the tree graph thing, that makes sense? Okay. So if you have the San Francisco office, the LA office, and the New York office, then obviously you're going to put the highest bridge priority on the New York office. So you will have all of these connected, and RSTP through an algorithm that I will hopefully explain later if I'm not using up too much time, will turn this link off to stop the storm from happening. So now, whenever LA wants to communicate with San Francisco, it'll have to go through New York. And that takes about as long as going to Germany. It's about, I don't know, 50 to 100 milliseconds. Whereas within California, it'd be more like 10 milliseconds. And that's enough to be annoying. But if you want to use L2 switching on your WAN, then you have to do something like this. So People will try to maybe move the highest bridge priority to LA or something and make this 3, but that's, clearly unacceptable. Um, well, because the LA is going to go down and then this one's going to take over. It's just so that makes sense, right? If you had L3, if you had L3 routing, then and you could deal with a graph, then these packets could go through directly. There wouldn't be no more need to turn this link off. It's okay so far? All right, so this next example, this is what I worked the hardest on right before the presentation. Um, I didn't explain this, but the purpose of RSTP is to turn links off to eliminate cycles in the graph and make it into a tree, which is what it did here. So I'm going to come up with a slightly more complicated shape. So everything that has any kind of a line at all, no matter what kind of extra mark like an X or a dot, these are links that you've purchased from the telephone company or run along the floor or whatever. And what I'm going to walk through is RSTP in this diagram has turned off this link to remove this cycle because this is the New York switch, so it's the head of the tree that it's established, and it's decided to turn off this link. What happens is for some reason the backhoe breaks this link and the network is no longer connected. So RSTP needs to turn links on and off to restore complete connectivity, but still not have any cycles. And it needs to do this in a way that there are no cycles generated, even briefly, because if there are, there'll be a storm. So RSTP is going to converge to this shape through 5 steps. Have I given enough background here? Can I go on with the 5 steps? All right. This thing's really nice. All right. So we're starting out with the shape that I drew on the first card. So this is a working link that's been turned off by RSTP, and this is a link that's gone away. RSTP will send a proposal. I hope I get this right. Anyway, it'll at least be close to right if it's not right. No, not yet. Right. I don't have excellent notes on the TCN, but it's what he's talking about is, where's my first card? When you make this change, there's going to be learned source addresses in the CAM, the content addressable memory. The routing table next to all of these ports in the switches will have learned information about how to reach stations attached to these switches. When you change the topology and eliminate this link, that information isn't valid anymore because, for example, this switch here, if it wishes to reach a station attached to this switch, now it needs to go this way while before it went this way. So in the process of doing the RSTP, there are TCN messages broadcast throughout all the switches that cause them to flush their learned station address information. And they just flood the packets all over again and relearn them. It flushes all of the information on a port at once. But what I'm trying to struggle through is how it decides to turn this link back on. So, and it has to do this without making any brief loops in the graph. So it starts with a proposal here, and this switch transmits the proposal to this one. And then this switch would like to agree to this proposal. But before it can do that, it has to turn off these two links. These two links are not ultimately going to be turned off, but during the convergence, they're temporarily disabled, just like this one. So this is step 2. And then once this is done, the switch sends an agreement. Maybe I should keep 2 on the screen at once. So this link no longer exists. I'm going to leave it blank. And these links have just been disabled. Disabled links are still allowed to send RSTP stuff. All links always send RSTP. This is the actual data packets that they don't send. So this switch will send 2 of these please disable everything proposals. And these switches, they don't do anything. They don't have any downstream links to disable, so they immediately agree. Does this make sense so far? So after the agreement, the link is turned back on. In a slightly better diagram, I would show which of these 2 switches is disabling the link. Because it's not the link itself that's disabled. It's one of these switches turns it off at its port. They don't both turn it off, only one does. But it's not important to get a feel for the algorithm. So here the proposal goes this way. This link is broken, and then it agrees. And we repeat the same thing along this link. And then after the agreement, this switch turns the link back on. And I don't remember where the TCNs are sent, if they're sent before, after, or during. I assume they're sent during, but there's a, it's not always necessary for the TCN to clear every bit of learned information in the whole network, but it usually ends up clearing more information than it needs to in theory, just because the protocol doesn't leave a way for the switches to know how little they need to clear. None of the switches have a complete picture of the overall network. All right, so you guys understand RSTP, sorta? So you can see how the combination of RSTP and the flooding learning will route around these failed links, and it will dynamically learn the locations of all the stations. And those are the two things that all these protocols need to do. Um, Before I go on, I think I need to give some background on um, hardware routers as opposed to Unix routers. They have some slightly different terms. Um, yeah, I don't know. I'll repeat it if it's not. Just go ahead.
Anyway, if the basically how when the link is broken, if that link were to come back on or something, how does RSTP then stop it from forming a loop when it's regaining the links?
Um,
Will the first one recognize the proposal chain or something?
the the MAC status, or maybe it's not even the MAC. I think it's either the layer 1 or the MAC. It's another confused. The green light on the back of your Ethernet card feeds into the switch's control plane where it decides all this stuff. And if you have an expensive switch like a Cisco that doesn't implement RSTP because it's too expensive, you can't afford the new one that does implement RSTP, then you'll notice the ports go orange for about 30 seconds. When that link state light transitions from dark to green, the port doesn't come up in a forwarding state. It comes up in a blocked state. And then the switch has to operate through this whole proposal agreement thing before it'll turn the link back on. So that would be, yeah, in the cars, the X was a broken link, and then dashed lines is a working link that's blocked. So the lights would be green on this link, but it would stay blocked. So I don't have a good example for a link coming back up, and it was a bit of a struggle to make this one, and it might not be completely right. But it goes through a similar process of when this link comes back up, if it's a better path, then this switch here will know a better path to the root switch, so it will send a proposal to this switch. And then this switch will turn off this link. And then it will agree and then bring up this link. So it's something like 1, 2, 3, and then
Bridgeport priority cost delivered.
what about the priority? Or, yeah, sorry I'm so dry. Is this more confusing or less confusing? I don't know. Anyway, all switches, even pre-RSTP switches, bring freshly connected links up blocked and then transition through some state machine before they start forwarding. And you can fool them if you have if you have this set up and you add this connection, this will actually screw them up. It's documented. They tell you don't do this, it will cause a storm. Because they can't watch the link state come up. They don't know when this hub has been connected. And God willing, once it's connected, they will be able to see each other's packets through the storm, and will eventually learn to turn off whichever one of these has the least favorable path to the root switch. And the storm will end, hopefully, depending on how expensive your switches are. I've never tried it, but it is explicitly warned against in the documentation. Is that maybe more helpful? All right. Any more questions on the index cards? No, no one has ever told me about anything like that, especially not publicly. Um, but y- you can set up VMware with a bunch of VMs underneath it. I know one person that tried to do that. I don't think it works very well. But, so, the commercial routing terms, people with Unix routers usually think that routing means forwarding packets, but this is a difficult term because real routers have the ports are in line cards. And then there's some kind of bus that all these are connected to inside the router. And then they have, they have brains in here. It's not just regular Ethernet chips. They have some kind of smarts. And then separate from this, there's the control plane, which will be a really slow and cheap CPU with not very much memory that they've charged you a whole lot for. And the control plane will snoop on this bus a little bit. I think it sometimes sort of acts like another port on the bus. And it will also send commands to the brains inside each of these line cards. So this is the forwarding plane. So if you have a router, an L3 router that has a packet coming in, and it needs to put this onto the forwarding plane and send it out, that's not called routing, that's called switching, at least according to one giant vendor. So a router doing this is switching, which is very much like what a switch does, which shows kind of what I'm trying to say about these layers not meaning a whole lot. The routing is more like what RSTP and the learning process do, of sending these commands into the line cards to tell them where they need to forward based on destination. So does that make sense? You understand the difference from Unix? So there's some other terms. There's the CAM, the fib, and the rib. By the way, I'm going to talk for a lot more than an hour, probably. What time is it? Excellent. Definitely not more than 2 hours. So the CAM, or for layer 2, or in this new stuff they're selling, they call it the TCAM. I don't know why exactly. This is the main part of the brains inside the line card. The control plane fills the CAM up with stuff. I think in switches it may be possible to fill the CAM without involving the control plane. I'm not sure. And then maybe when the TCN comes through, the control plane tells the line cards to flush the CAM. The fib is sort of like the TCAM. The control plane keeps inside it a list, sort of like that learned list of destination, port, and next hop. And so if this is like port 1, 2, 3, then it'll say if you want to reach this is what the Unix people call the routing table, is the fib. And the rib is a series of other routing tables maintained by the protocols that I'm about to talk about. And not all the entries in the rib make it into the fib. So you can have multiple routing tables running at once and they feed into the fib. But for the purpose of our simple discussion, these are almost collapsed. So the dynamic routing protocol will establish the fib, which will be loaded into the CAM or TCAM in the line cards and cause the forwarding to happen. Is this it's okay? The difference from Unix makes sense?
So it sounds like the CAN is the fib loaded to memory and some kind of quickly accessible memory structure, hash table or something. Or it's basically the same information.
Yeah, I think that sounds fair. My impression is that the fib stored inside the control plane is in normal memory, and at least parts of it will be loaded into special memory in the line cards that's not regular DRAM, and that's the CAM or the TCAM. So when Cisco tells you that they are process switching a packet, then that means it has to go to the control plane, which looks it up in the regular fib, and then sends it by hand out of a line card, rather than, okay. He said when it's in the TCAM, it's called hardware switched. Um, so I don't have index cards for OSPF, but it has some character that makes it harder to make index cards of because it's not synchronous the way that the RSDP and flooding learning is. Um, so these are 3 OSPF routers and 3 links between them. Over these links, several things will be happening at once. They will be sending hello packets, and they all send these to each other about once every 10 seconds. And they will be sending database discovery packets, or in others they'll be called something else. This is what's flooded in OSPF. So in the switch network, you flood the packets when you don't recognize the destination. In OSPF, you flood routing information. So as you know, with the regular IP network, you'll configure by hand subnets onto each router. And these subnets are flooded over these links in the database discovery packets with a protocol where it'll send so this router will say, I have this attached, and the other router will say, okay. And then this router will say, and then this one says, okay. So this router will advertise the subnet in this direction, and then this one will copy it in this direction. And they have version numbers to help and not send too much of this information. The database discovery process is really complicated, and I didn't prepare enough to understand it. Go ahead.
Are those two bottom routers AVRs, or is it just all part of the same area?
Yeah, I didn't do anything with areas, all one area. So these are the only 2 kind of packets actually transmitted. And then the third step, which again runs not synchronized with these other 2, is the Dijkstra algorithm. So the hello packets are sent every 10 seconds, no matter whether the database discovery packets are flowing or not. And the routers learn about their neighbors through these packets and then send out the database advertisements. These packets build within each router a picture of the entire network. And because the packets are flooded, the picture contained inside each router is identical. So they all have the same picture of the network. And this algorithm runs separately on each of these to produce the fib. So all OSPF routers have a complete knowledge of the entire network. And the problem that you can see with this from the perspective of switches is these database discovery packets are going to take time to send, and not all the routers are going to have them at the same time. And because these two processes are disconnected, it's not true that the Dijkstra algorithm runs every time a new database discovery packet is seen. It runs periodically. It runs until it finishes before it runs again. And new DD packets could come in while the algorithm is running. So if there are a lot of changes, the fib is always a little bit out of date. If there are too many changes that happen too quickly, it won't work, which is the same that's true of switches because it turns off those links. But the reason that these can be disconnected is because layer 3 has an IP TTL. So if the fib here is not equal to the fib here, it's possible that a packet could loop between these two routers, but it'll only loop about 30 times and then it'll be dropped. So it's normal in layer 3 routing to have temporary routing loops. And the whole design of the algorithm is changed because they have this IP TTL. The other thing that's interesting about having a graph rather than a tree is, I think maybe I need one more layer for this example, but both switching and OSPF can to some extent split packets going from here to here, some down this route and some down this route. In switching, you have to configure it manually. The only way it can work is you have two links here. And you manually bond these links together into some kind of channel. And it's not like it sends one bit down one channel and one bit down the other channel. As I understand it, it uses a hash of the destination MAC address. So, a packet to station A will go over here, and packet to station B will go over here. And everybody uses these hashes. But in OSPF, I can send a packet to station A here, and B over here. Because it's not a tree anymore, it's possible to balance traffic over more than one hop. Does that difference make sense? You ready for this? You want to ask questions about OSPF? You guys are all kind of questioned out. All right.
In the DB process, will router A, send information to router B, or subnet to router B,
The question is, in database discovery, will router A send off information to some third router about a subnet attached to router B? And the answer is yes. And they have some kind of synchronous information acknowledgement that they'll keep their databases in sync. And I think they have some way that it uses less and less bandwidth. Like it'll say, I already have the following LSAs, and it'll give it a list of like 20 of them. And then the other end will say, I would like numbers 19 and 7.
Would it move around or would it stop everything else unless he's
The information itself it's absolutely flooded, but it doesn't just say, I have subnet A. What it says is, my latest database has the following LSAs. It has numbers 1 through 50, and it has 70, 71, and 72. And then it'll say, this is my latest database in one big packet. And then the other end will say, have almost all of that except for 15. And because you can stick them together in packets and because of this whole acknowledgement thing, it turns out that it doesn't just use up an infinite amount of bandwidth. So I don't know, you're telling me stop, which I could do. I got an email from the speakers that said since it was the last talk that I could go until cleanup, which would be longer. All right, cool. You guys can bail out if I'm boring you to tears. Yeah, yeah. Anybody want to? If you want to go to closing, it's all right. Yeah. It won't be the first time I was lied to, but yeah. So the punchline with ISIS in 5 minutes is all about the different way that the OSI people address nodes. This is not IP, it's a different address format. So if I can just find, just in a hurry, I'll just, these are my notes. I was going to draw this out by hand. So this is 1 byte wide, and this is m bytes wide, n bytes wide, OOP. The AFI is, I think it's almost always 47, and the AFI implies how big this is, like where this boundary is, how big is m, how big is the rest. Yeah, so I should write bigger, but. Is there really?
It's a little blurry. Keep going. Other way. Good. Yeah, that's fine.
Okay. So this is sort of like subnets in IP. The system field either is equal to or is derived from the MAC address. So every station will have a globally unique system field of about 6 bytes. And the IDI through the HO DSP is something like your ASN. So it's unique within your organization or within most of your organization. So this is always the same, it's constant. And then this is your subnet number. But the subnet number has a special meaning in ISIS. You can have the same subnet attached to many routers. And there is this is an
See what you're writing anymore.
if these are hosts and these are routers, the address of this thing will be, is it 46 or 47? It'll be 47 dot, yes, whatever, dot, area 5 dot, A, B, C, whatever. All right. Fair enough. Thanks a lot, guys. No time for more questions.
Whoa, yeah.